And as the Directorate looks forward to its next 100 years, AIT is pleased to welcome this panel. So please join me in welcoming Dr. John Russell.
Good afternoon, everybody, and thanks to SME for letting me come up here today and speak and to bring this panel up so we can talk about some exciting things going on in the Air Force Research Laboratory in the past as well as in the future. Okay, so the first question I get is, the Air Force isn't even 100 years old, so why are you guys celebrating your 100th anniversary? So it all goes back to the fact that the Air Force was a part of the Army. If you look at the history, the Wright brothers flew their first plane in 1903. The Army bought their first airplane in 1909. And after they bought the plane, they decided they needed to do some research to improve flight, to improve the materials. So back in 1917, Congress actually created a materials section within the Army Air Corps to develop specifications for existing materials for aviation and to research new ones. So from those humble beginnings in 1917, the Air Force Research Laboratory's Materials and Manufacturing Directorate is a national asset. We do cradle-to-grave development of materials and manufacturing processes, all the way from the basic research of fundamental materials in ceramics, metals, polymers, semiconductors, and even biological materials, through applied research, through the development of manufacturing in conjunction with the Defense Industrial Base, and even to follow those materials into the field and research when things go wrong in the field, what happens to those materials, were they a cause, and how do we fix them? And my part of the AFRL Materials and Manufacturing Directorate is the Manufacturing and Industrial Technologies Division. We're actually called out in law that the Secretary of Defense shall have a manufacturing technology program. We've got three key things that we need to do to deliver technologies for the Defense Industrial Base and our warfighters. First is to develop transformational manufacturing processes, things like additive manufacturing and the digital thread, and apply them to defense problems. Second is we need to be a transition partner for all of the technologies coming out of the Air Force Research Laboratories, things like advanced sensor pods, like the LCAT, the low-cost attritable aircraft technologies program. And finally, what we're really known for is to work with our acquisition and sustainment programs to help reduce the cost of those systems in development and out in the field. We're just in the midst of wrapping up a major multi-year investment working to reduce the cost of the F-35. Now we're looking to the future, some of those new planes that are coming out from the Air Force, a lot of them classified, to drive down their costs as well. So we have had a tremendous impact in the Manufacturing Technology Division over the years. The program was first stood up on law in the late 1940s, and since then we have had a major impact not only on the Air Force and the Defense Industrial Base, but really the industrial base as a whole. Sorry for the formatting errors there. I'm not going to read this chart, but just a quick snapshot of a lot of the things we do. Now I'm going to go into just a few selected highlights from this list to give you an idea of what we've done. So NC machining has its roots in an Air Force-funded project back in the 1950s. The Air Force actually had a contract with MIT to try to enable easier machining of complex geometries in 2D and in 3D. The technology was first demonstrated in 1950, and industry finally started to develop their own machine designs in 1955. You cannot imagine today trying to do modern aerospace production without NC machining. There's just no ways some guy with a manual drill bit could do the things that we ask of the industrial base today. We do a lot with the sustainment side of the Air Force as well. Spare parts is a big issue for the Air Force. If you look at the rotors and turbine engines, the original plan was that these things would have a certain life. After 5,000 tacks or 10,000 tacks or whatever, you would just throw that part away because it had reached the end of its design life. But we knew that a lot of these rotors still had significant life left. So we worked to develop fatigue crack models. We worked to develop non-destructive inspection tools to determine how much life was left in these discs to see if we could get another maintenance cycle or 2 maintenance cycles out of these discs. And this just had some tremendous cost savings for the Air Force to the point now where we can't even keep track of the cost savings involved. Everyone knows what Lean is. First deployed as the Toyota production system. And it certainly has made its way throughout the automotive sector and a lot of industrial sectors. But in the 1990s, the defense industrial base really did not take advantage of the Lean principles in general. So in the late 90s, we established the Lean Aerospace Initiative in partnership with MIT and a host of industrial companies to take a look at how we could take Lean and put it into defense production. A couple highlights you see in the chart here. First is the Joint Direct Attack Munition. Following the Second Gulf War, we needed a lot of JDAMs to be replaced, and the factory really just was not capable at the time with their current processes. So we sent a team in there to work with Boeing to lean out these processes and to really get them up to rate and to be really a modern production facility. The other side of the coin is the sustainment side of the Air Force. So if you've ever been to one of the Air Force depots at the time, a lot of people doing a lot of hand work, not necessarily efficient. We started off with pilots on some maintenance stations on the C-5 and the F-15, and that has changed into today where the entire maintenance line for almost every Air Force depot is founded on Lean principles. And we've greatly increased our throughput, which means that we have more airplanes available for our warfighter today. Something that's near and dear to my heart is the work that we've done over the years in organic matrix composites. Well, certainly AFRL has had its hand in the development of composite materials in general for aerospace. ManTech in particular has taken those materials and made them a true industrial process. Our work in sponsoring funded research with the industry on fiber placement is now in wide use today. You can't build an F-35, a 787, or an A350 without the use of fiber placement. We've also helped launch the current generation of autoclave materials in host with the AFRL S&T side of the business, as well as DARPA and some other entities. At first we did them for low volume aerospace production, and they're slowly making their way into new aircraft today. We've helped develop the design and manufacturing processes to enable these large-scale composites. In fact, the design of the 787 barrel has a lineage to some design work that we did with Boeing back in the mid-1990s. Then finally, one of the shining stars of what we did was the Composites Affordability Initiative, where we developed the design and manufacturing processes to enable large, integrated, and bonded composite structures. This $150 million program developed design tools, the manufacturing methods, quality assurance tools, and large-scale demonstrations to prove the feasibility of bonded composite primary structures. And the capstone of all that was the X-55A Advanced Composite Cargo Aircraft. One of the things that we're known for is to be the godfathers of the manufacturing readiness assessment. Back in the mid-2000s, we got a lot of grief from the big Air Force that, well, hey, this technology is TRL-6. How come we're having such a problem once it gets to our system? Well, just because something is at TRL-6 doesn't mean it's manufacturable. So we developed, in conjunction with a team of folks across DoD, the manufacturing readiness levels and the threads underneath them in order to make sure that you know how mature your manufacturing processes are. These are now standard operating procedures for major weapon systems. They have to meet certain MRL milestones as they get to certain acquisition milestones. And we're also developing tools so that even the early 6-1 research can start to think about manufacturing as they move forward. So really the bottom line is what we're judged for in the manufacturing technology division is our impact on the weapon systems. Here's some examples of the weapon systems I can talk about here. As you can see, going back as early as the F-16, we have had significant impact on reducing the cost of these airplanes. $1 billion over the life of the F-16, $800K for the B-1, $350 million for the F-22, $3.2 billion for the F-35. Really some just astounding numbers. And we've touched everything from wiring to metal processes, processes for turbine engines, composite materials, all across the board. So that's a look back at our past, and we're certainly proud of the work we've done over the past 100 years. But you need to look to the past to think about what's going to happen in the future. So there's a lot of challenges now as the Air Force moves forward. And so what's next? First of all, the Air Force has designated several technologies as game changers. How do we fundamentally change the way we fight to keep the fight unfair in our advantage? Hypersonics, so we have to go really, really fast. Mach 5 plus. It's going to have a big impact for what we do, significant manufacturing challenges. Directed energy. Everybody would love to have a gun that doesn't run out of bullets, and that's what directed energy has the promise to be. Autonomy, a lot of people think autonomy and they think of drones that fly themselves, they think of the Terminator or things like that. But it's more than that. It's about having that R2-D2 in the back of your X-Wing to help Luke Skywalker, the pilot, do his job. It's about having maybe a fleet of unmanned air vehicles alongside the wings of an F-35 or an F-22 to help augment what that pilot can do. Nanotechnology certainly has had a lot of promise, and since really starting to gain traction in the mid-1990s, the Air Force is still looking to that today. Then unmanned systems in general. I mean, there are a lot out there now, but I think we're just scratching the surface in terms of what we do with them. Another thing DoD-wide that people are looking at is called the third offset. Again, this is a way to take a look at a fundamental change in how we operate as a warfighting force. The first offset technology being nuclear weapons when faced with superior numerical disadvantages as we look to the Soviets across the East German border. The second offset being a combination of stealth, precision-guided munitions, and GPS. And this third offset, they're looking into learning machines, human-machine collaborations, and assisted human operations, kind of the things I alluded to with the autonomy coming out of AFRL. So those are the warfighting concepts we're looking at, but we're also taking a look at what are some of the trends going on out there in industry. Certainly, Industry 4.0 and the brilliant factory concepts are things we're keeping an eye on. How do we take those kind of concepts into the defense industrial base to take full advantage of that? So with all that, some future strategic focus areas we have. The top is more technology-wise. Certainly additive manufacturing has big promise. It can change the way you do business. You can actually make parts that you can't make with conventional means. So how can we take advantage of the infinite design flexibility we have with additive to do some unique things to improve the capability of our systems? The digital thread, so that manufacturing gives off the most data of any sector of our society. How do we take that data and do something actionable with it so that we can improve not only how we manufacture our systems, but how we maintain them throughout their life cycle, whether it be a 20-year cycle for a Predator or a 90-year cycle for a B-52. And robotics, certainly robotics is a very mature technology, but as you look to aerospace, we're only going to build 100 of the next bomber or 100 of the next tanker or transport. How do you make robotics affordable in a low-rate production environment? How can we get them to be more flexible, more easily reprogrammable? How can a robotic cell be able to do multiple things so that you can reduce your non-recurring costs? And then warfighting-wise, there are several things we need to keep our eye on. First of all, hypersonics. Right now, the industrial base for our hypersonic cruise missile does not exist. And the Air Force has some ideas of launching a program of record in 2020, and that's not that far away. How do we get these exotic materials that withstand the temperatures required for hypersonic flight to be manufacturable in the size and quantity that we need to field some kind of system. Directed energy, another big deal, it's all about size, weight, and power. How can we take this concept of a Star Trek phaser beam, put it in some kind of pod that can be flown off an airplane wing or in the belly of the next generation fighter, and also get the power off the engine to operate not only the engine, but the directed energy weapon. It's going to be a big challenge. I talked about the low-cost attritable aircraft earlier. LCAT is a very unique concept where you have a UAV that's so cheap, you don't worry about if it's broken or if it's shot down because it's easily replaceable. So now you can have a swarm of these things go in ahead of the exotic, exquisite systems like the F-22 and the F-35, punch a hole through the enemy defenses. The good thing about this is that we've got a lot of restrictions that come off. This does not require depot maintenance. It does not require to go through the airframe structural integrity program. So your design space and your manufacturing space has opened up significantly. You can do a lot of very unique things. Now we can take advantage of techniques to build cars for some of these things. Then finally, we are the Air Force. We are still going to be flying stealth airplanes. Those next generation systems out there are going to require very high precision manufacturing beyond what we're doing today with the F-35. So lots of challenges ahead. So in summary, the Air Force's manufacturing technology program has made some enduring savings to the Air Force weapons systems over the years. We've achieved significant payback of the program. And as you look to the future, this agile manufacturing is going to be critical to achieving more savings in the future.